Holy cow, we are so close. Guys, we're in our last unit. This is so nuts. I didn't think we'd get here. It was such a huge task to make all of these videos, but we made it. This is our last unit. Like, not just calculus, but like the entire course. Four more videos. That's it. And this is our first of those four. Optimization. So you're like super close to like sun, ice cream, beaches. I don't know, swimming. What else do you do during the summer? Eat, sleep. Oh, yeah, sleep. You're very close to sleeping, having a lot of time to sleep. Okay, Unit 9, optimization. The first time you guys have ever seen this is when we mentioned it in grade 9. Actually, maybe you guys have seen it in elementary school, but I'm not sure. We pose questions like, okay, let's say that you're working for Coca-Cola and you want to make some sort of like a can. It can have a volume of 350 milliliters. I think that's like a standard can of Coke. I don't know. I don't really drink Coke anymore. So 350 milliliters, it has to contain that. But obviously, you don't want to make like a ginormous can because then you're going to waste all your money with paying for aluminum, right? So you want to minimize the surface area. And that's what we mean by finding the best, like find the maximum or minimum of something. And so start designing it. Like in grade 9, we got you to test a couple different shapes. So, I mean, we have shape number 1, shape number 2, like maybe that's what your can will look like. I mean, it's like a dish, but okay, that could be like your second one. And then maybe your third one is like a pipe almost, you know, teeny weeny. But they should all be able to fit 350 mils of volume of Coca-Cola inside. However, like you'll notice that each one of them looks slightly different, and so the surface area might be better in some and not better than others. Okay? What we're going to do now is we're actually not going to do trial and error. Okay? We're actually going to do derivatives. I I'm teaching grade 9s right now, and I really this is so hard to teach them. Trial and error sucks. Okay? And so I really want to teach them, hey guys, do you know what a derivative is? But c'est la vie. Okay, since you guys learned about maximum and minimums, just use local extrema. And we do that, like your max and mins, by taking the first derivative, setting it equal to 0. That's basically what we're doing. Okay, so what we want to do, and let me throw an example at you. Example number 1, find the angle. Find the area of the largest rectangle. So they want us to maximize the rectangle. That right there, what they're telling you to maximize, is the formula that will be your original formula. That's what you're going to take the derivative of later. They're also giving you some numbers. And so the number that they give you, the perimeter, is not what you're maximizing. That is like some sort of a limit. It's limiting you. It's your restriction or your constraint. Okay, so to start off this type of question, what you need to do first is draw a diagram. Take a look at the diagram off to the right. It's a rectangle, length and width, pretty standard, right? You also want to make sure that you add some let statements because obviously you're going to use some variables. Love to know what those variables mean. Okay, so L for length, W for width. Now, we want to start forming that equation that we're trying to maximize. Obviously, because it's a rectangle, area is going to be length times width. This guy is going to be my function that I'm trying to take the derivative of. So if you try right now, your derivative is going to look weird. You have an A, you have an L, and you have a W. How do you take the derivative of that? There's too many letters. That's where your constraint comes in. Okay, so using your constraint, I'm going to move down all the way over here. We know that the perimeter is 200 meters. That means that I have a perimeter formula, right? 2 lengths plus 2 widths should give me the perimeter of a rectangle. We're going to make that equal to 200. And I can solve for one of the letters. It doesn't matter which one you solve for. You can solve for length or width. And so I just decided to solve for width and bring everything to the other side. So this is my width. And now that I have what width is, I can take out that width and put this guy instead. Then I'll have only 2 letters. and that's what you want in order to take the derivative. Okay, so let's go through that again. You want this because that is what you're going to be taking the derivative of, but too many letters. Use your constraint to eliminate one of those variables and have it down to 2 variables, then it makes it much easier to do the derivative. Okay, so here we go, length times width. Get rid of the width and put 100 minus length instead. Then you're going to simplify it. All right, and then you have your final area formula. That looks beautiful, and there's only 2 letters, your area and your length. Now it's ready for you to take the derivative. Okay, so taking the derivative means a prime, but in this case, like I really do want to show you, just so that you don't ever say that you've never seen it, because they do use this in university quite a bit, the derivative of your area with respect to your length. Okay, so dA over dL is the same as a prime. You're doing the derivative of your a with respect to your L. Okay, so taking the derivative of this function is going to give you 100 minus 2L. Setting it equal to 0, and then you solve for your length. Okay, so bring the 2L to the other side, becomes a positive. Divide both sides by 2, and you get your length. Now, what did you just find? Your area is going to be maximized when your length is 50. Okay? We could actually check to make sure that actually results in a maximum. You can do that in 2 ways. You can either do an interval chart, which takes a little bit more time, or I would actually recommend maybe doing a second derivatives test. So that's where you take the first derivative and do the derivative again. So you have d2a over dl2, which is your a double prime, okay? And it gives you -2. If that number is a negative, you get a concave down. That's what a second derivative tells you. So a concave down means that you have a maximum at the top, and you've just verified that yes, length of 50 will give you a maximum. So that's what this test is for. We're just making sure that it actually is a maximum. Because if you get, say, a +2, then you're going to get a minimum, a concave up, which means that you probably did something wrong because the question itself said that you had a maximum area. Okay, let's keep going. The question itself said, I want you to give me what that maximum area is. So we haven't quite figured out that answer yet. All we figured out was when it happens. So the maximum area happens when your length is 50. So let's put that back into our formula and find the max area. That means that our maximum area is 2,500 meters squared. You could do a quick check and check your constraints. And so taking the 50 and putting it back into the length, you want to just make sure that your width is like a normal number. So this was the width formula that we got from the constraints at the beginning. If we make L a 50, your W is also a 50. That's like a normal number. If your W ended up to be like -50, then you'd be like, okay, well, that doesn't make sense. And you could then say, I probably made a mistake somewhere, and just check your work again. The question itself did not ask you for your dimensions, but if they did, you would know, okay, your area is going to be length times width. And so you're going to get 50 for your length by 50 for your width. And in your therefore, you would just say the dimensions are 50 by 50 meters. So that's how we tackle a question, and they're pretty much the same steps all throughout. So let's try 2 more questions. This is example number 2, and you've probably seen it like a million times. A rectangular field is to be fenced along the bank of a river. So no fence is required along the river. I don't know why you would put a fence there. Technically, you only need 3 fences. So one here, which is your W, one here, which is your length, and then one here, which is also a W. The amount of fencing available is 100 meters. That really looks like my constraint. That didn't have the word maximum or minimum anywhere near it. Find the dimensions of the field having the largest possible area. So I see the word largest and I'm like, okay, you're looking for an optimization. I need to take the derivative, set it equal to 0. They told me that I want the largest possible area. So that is the formula that I'm going to take the derivative of eventually. Okay, so the area, obviously we're talking about a rectangle, so the area is length times width. We have our diagram, we have our let statements, and then the constraint. So again, the constraint is for the fact that I can't take the derivative of my cloud right now. There's too many letters, A, L, and W. So by using the constraint, which they said one W and another W, so two W's, and one length must be 100 meters. So two W's plus one length is 100. I figured it'd probably be easier just to solve for L, and so I brought this guy to the other side. You could solve for W if you want to, but you might get fractions. So I don't like fractions. Once you have your L, you can take this guy, get rid of your L, and sub it in instead. Okay, so let's take a look at the solution now. All right, first you want the area formula because that's what you're going to take the derivative of. So notice that I got rid of my L and I put in that constraint equation instead. Okay, I'm going to expand and simplify. So I get my area formula with only two letters. You have your A and your W, no more L's. Then it's easy to take the derivative because at this point, I want to start finding those local extrema. Derivative of this guy is going to be 100. Derivative of this guy is going to be negative 4W. All right, notice that it's changed the derivative of your area with respect to your width because we have W's. All right, setting that equal to 0 and bringing the W to the other side so that we can solve for any critical values. And I get a critical value of my width of 25. So at 25 meters for the width, you're going to have a maximum area. Although I think I'm just saying maximum area, I could have a minimum area, and that's why we do the second derivatives test. Take the derivative of the derivative, so the second derivative will give you negative 4. That's going to be less than 0, which gives you a concave down, which is a maximum. That means a maximum is happening when your width is 25. That's exactly what we were looking for. Maximum area. This is happening at a width of 25 meters. Okay, so the question itself, if we go back up, I'm not going to, but if we did go back up, they asked for the dimensions. They didn't actually ask us what the maximum area was. They just said, what dimensions make that happen? So you've already solved for this guy, your width, which is 25. Okay, this width is 25. Obviously, if all three of those have to be 100 because we don't have this side, that's water, right? Is going to be 100 minus the two 25s, so your length is going to be 50. I guess I should do that the same way I had written it before. All right, so the dimensions are going to be 50 meters by 25 meters. This is going to be your width. This one is your length. All right, let's do the last one because I think you're getting the hang of this. The way that I can make this more difficult is if I make the shape more difficult. So now we're not talking about just a rectangle. We're going to throw in kind of like a semicircle too. A Norman window consists of a rectangle surmounted by a semicircle. So notice that the rectangle I've labeled in blue A1, and then the semicircle is A2 at the top. Find the shape that will admit the most light. Okay, so what are they trying to maximize here? Most means maximize. Allowing the most light means you want the window, like the window itself. That must mean you're talking about area. So you're trying to maximize the area here. The perimeter of the window has to be 14, so that's my constraint. Okay, so diagrams off to the right-hand side, left-hand side, they've already given us our let statements, which is great. I want to show you where I actually got my formula from. So I want to maximize the total area, and the total area is A1 plus A2. So this is what I'm trying to maximize and start to do derivatives of. But where did the rest come from? Okay, so this guy's area is going to be length times width, right? And since we don't have length, we have height. That's going to serve as my length. And so I'm going to put this, and that's just going to be HW, which is written right here. I hope that's okay. The other one, finding the area of half of a circle. So you're going to go pi r squared and 1/2 of that. They did tell you something before, which is actually written in brackets right here. And let me just go through that really quickly. What they said was, I'm going to get rid of this so that it's not in the way. Note, W over 2 will represent the radius. So this one right here, W over 2 is the radius. Or you can say R for the radius and then the width would be 2R. So, okay, let's break that down. If this is W, then obviously your radius is going to be W over 2. So you can use those letters, or let me get rid of all of that. If you decide instead to call this R like a regular radius and not this, then that means that you have to say that this is not W, it's 2R. So you choose, are you going to use W's or R's? I myself am thinking of maybe using just W's because that's what was in the diagram already. So let me get rid of all of that. Okay, so going back to my half pi r squared. That's going to be the area for half of the circle. And so 1/2 pi r is going to be W over 2 squared, which is 1/2 pi W squared over 4. And that's what you see right here. Okay, so that's going to be your A2. Adding those together gives you your total. And so I just simplified the 1/2 pi W squared over 4, and that gave me this. And I still have the HW. Okay, so I'm supposed to maximize that equation, but there's too many letters in it. You have an 8, you have a W, sorry, that's a H, and that's a W. All right, so 3 different letters you can't take the derivative of. It gets really complicated. That's why we have our constraint. So our constraint is going to allow us to write one of the letters in terms of another, get rid of it. So we have our shape, and let me go over that one more time. You have an H, you have a W, you have another H. So H, H, and W. The perimeter would be 2 H's and a W. So far, so good? Then you have a half circle. Half circle, let's see, perimeter or circumference of a circle is 2 pi r, but since it's a half, divided by 2, which means it's just pi r, and you know that r is going to be W over 2. Okay, so here is the half 2 pi r, and that r is going to become a W over 2. These two cancel out and you get a 1. Okay, I'm thinking that, you know what, because there's only the one H up here and there's actually 2 W's, it'd make more sense to just write the H in terms of a W instead of switching those 2 W's into H's. So I'm going to solve for H and then have everything as W's. Bring all of this stuff to the other side so that you have 2H left by itself, and then divide everything by 2. So this is going to be my height. I'm going to get rid of this guy and put that instead. Okay, so here is the solution. My area formula, get rid of the H, put what we just found through our constraint equation. Okay, so this just W is right here. All right, multiplying in and simplifying will give you these guys. We still have the pi over 8 W squared on the right-hand side. Then what I'm going to do is start putting things together, and I notice that these two are like terms. And so I put those together in radians, but I'm also noticing that these guys are also like terms. So I could leave them like that and take the derivative. I am so sorry. Why do they always do that? Did that freak you out? I apologize. That is the doorbell, I think, for like the custodians or something like that. Someone's making a delivery. My mistake. Is it too late to tell you guys not to have your volume up too high? Okay, so I factored out just the coefficients, and then I had the w squared on the side. So this is our area formula. We're going to take the derivative with respect to your width, okay? And so we get something like this, and I'll show you how we got that. 7w is going to give you just a 7. Taking the 2, doing the power rule, and multiplying this entire coefficient, because that's just numbers, right? That's just one number. So 2 times that entire thing, and then subtract 1 is going to give you the exponent 1. Setting it equal to 0, I'm going to start to solve for w, and w is kind of nice and by itself, which is great. Bringing this entire thing to the other side becomes a positive, and then dividing the 7 by 2 and then that entire bracket. So solving for that, I get w is equal to approximately 3.92. And again, that could be a max or a min. We don't know. So we'll do a second derivatives test by taking the derivative and doing the derivative again, getting a second derivative. I got a negative number, and so that's less than 0. It's going to be a concave down, which gives us a max at that width. Okay. So the very last part is, because they told us what shape would actually give us this maximum light, they're asking us, okay, what kind of dimensions are you talking about here? So we do have some of the dimensions. We had our width, that was, what was it, 3.92 meters, I think. And then we have our heights, which we can find. Just take your W's and put them back into the H formula. Okay, and get 1.96. 1.96. This guy you don't have to tell the dimension of, but you might want to tell me what the diameter is. So you can just say, here's your width, here's your height, and that one's going to be your diameter. Okay, so I think you can see a pattern between all three examples. You're essentially just taking, like, you're finding your local extrema. That's it. You're taking your derivative, setting it equal to 0, and just solving for your dimensions. I'm so sorry for scaring you and freaking you out with the doorbell, but I'm also too lazy to make another video. So have a great day, guys.